In our R console, let's start by loading our dataset. Don't forget to make sure you're in the directory containing the file wine.csv first. We'll call our data frame wine, and we'll use the read.csv function to read in the data file wine.csv. We can look at the structure of our data by using the str function. We can see that we have a data frame with 25 observations of 7 different variables. Year gives the year the wine was produced and is just a unique identifier for each observation. Price is the dependent variable we're trying to predict, and winter rain, average growing season temperature, harvest rain, age, and France population are the independent variables we'll use to predict price. We can also look at the statistical summary of our data using the summary function. This gives us information about the range of values for each variable in our dataset. Let's now create a one-variable linear regression equation using average growing season temperature to predict price. We'll call our regression model Model 1, and we'll use the LM function, which stands for linear model. This is the function we'll use whenever we want to build a linear regression model. Then inside parentheses, type price, our dependent variable, and then a tilde symbol, and then average growing season temperature, the independent variable we'll use in this model. Then, after a comma, we need to add data equals wine to tell the LM function what dataset to use to build the model. We're saving the output of the LM function to the variable named Model 1. So when we hit enter, we didn't see any output because it's been saved to the variable Model 1. Let's take a look at the summary of Model 1. The first thing we see is a description of the function we use to build the model. Then we see a summary of the residuals or error terms. Following that is a description of the coefficients of our model. The first row corresponds to the intercept term, and the second row corresponds to our independent variable, average growing season temperature. The estimate column gives estimates of the beta values for our model. So here, beta 0, or the coefficient for the intercept term, is estimated to be negative 3.4, and beta 1, or the coefficient for our independent variable, is estimated to be 0.635. There's additional information in this table that we'll discuss in the next video. Towards the bottom of the output, you can see multiple r squared, 0.435, which is the r squared value that we discussed in the previous video. Beside it is a number labeled adjusted r squared. In this case, it's 0.41. This number adjusts the r squared value to account for the number of independent variables used relative to the number of data points. Multiple r squared will always increase if you add more independent variables, but adjusted r squared will decrease if you add an independent variable that doesn't help the model. This is a good way to determine if an additional variable should even be included in the model. We'll also discuss other ways to select important independent variables in the next video. Let's also compute the sum of squared errors, or SSE, for our model. Our residuals, or error terms, are stored in the vector model1 $residuals. By hitting enter, we can see the values of all of our residuals. We can compute the sum of squared errors, or SSE, by taking the sum of model 1 residuals squared. If we type SSE and hit enter, we can see that our sum of squared errors is 5.73. Now let's add another variable to our regression model, harvest rain. We'll call our new model model 2, and again we'll use the LM function to predict price, but this time using average growing season temperature and harvest rain. When you want to use more than one independent variable, you can just separate them with a plus sign like we did here. Then we again need to indicate that the data that should be used is wine. Let's take a look at the summary of our new model using the summary function. We have a third row in our coefficients table now corresponding to harvest rain. The coefficient estimate for this new independent variable is negative 0.00457. And if you look at the r squared near the bottom of the output, you can see that this variable really helped our model. Our multiple r squared and adjusted r squared both increased significantly compared to the previous model. This indicates that this new model is probably better than the previous model. Let's now also compute the sum of squared errors for this new model. So SSE equals, and then sum of model 2 residuals squared. If we type SSE, we can see that the sum of squared errors for model 2 is 2.97, which is much better than the sum of squared errors for model 1. Now let's build a third model, this time with all of our independent variables. We'll call this one model 3, and again use the LM function to predict price using average growing season temperature and harvest rain and winter rain and age and France population. Again, we need to tell the LM function to use the dataset wine. Let's take a look at the summary of model 3. Now the coefficients table has 6 rows, one for the intercept and one for each of the 5 independent variables. If we look at the bottom of the output, we can again see that the multiple r squared and adjusted r squared have both increased. Let's now compute the sum of squared errors for this new model. SSE equals the sum of model 3 residuals squared. If we type SSE, we can see that the sum of squared errors for model 3 is 1.7, even better than before. In the next video, we'll determine if we should keep all of these variables in our final model.